Chemical reactions. We talk about four basic kinds of chemical reactions of alcohols. So alcohols are flammable. In the combustion reaction, we don't need to talk about too much. It's going to follow the same pattern as with other hydrocarbons. You've got your alcohol. It's going to react with oxygen, and the products will be carbon dioxide and water. Not much to say about that one. Okay, intramolecular alcohol dehydration. Well, this is starting to sound fancy, isn't it? Dehydration. D means removing. Hydration is water. We're removing water. So this is a chemical reaction in which the components of water, hydrogen and OH, are removed. They can be removed from a single reactant or from two reactants. In intramolecular dehydration, there's one reactant. So here's an illustration. Here we have a single molecule, and we're going to remove the components of water from this one molecule. So we're taking the hydrogen from here and the hydroxyl group from here, and those are going to make the water. And what we have left here is a double bond. Now this looks like the opposite of a hydration reaction of an alkene, doesn't it? If we started over here and we're adding water, that was a hydration addition reaction. This is just going backwards. Intramolecular means it's happening within one molecule. So like intramural sports, you play against other teams at your school. Intercollegiate is between schools. So this is within one molecule. The product ends up being an alkene, and typical reaction conditions are going to be 180 degrees Celsius and a sulfuric acid catalyst. So here's a generic example. Here we have an alcohol. We're going to remove the OH, and we're going to remove the hydrogen from a neighboring carbon, and we'll end up with a double bond and water. So here is one propanol. We're going to remove this OH group and a hydrogen from the next carbon, and we're going to end up with propene and water. Oops. Intermolecular alcohol dehydration falls into a category called elimination reactions. So we talked about addition reactions where you're adding something. The opposite is where you're taking something away or you're eliminating something. So an elimination reaction is a reaction in which two groups or atoms on neighboring carbon atoms are removed or eliminated, and the result is a multiple bond. So here we've got group A and group B. We take those off, and we get a double bond here, and A and B go off together. So dehydration is where we're removing water. We'll see some other examples later on where we remove something else. So elimination reaction is the broader category. Sometimes we can have more than one product that's formed, just like when we had unsymmetrical addition reactions on the alkenes. So let's look at 2-butanol. So there's butanol, it's 4 carbons, hydroxyl group on the second carbon. Now when we do a dehydration on this, we're going to take the hydroxyl group and a hydrogen on a neighboring carbon. Well, there's 2 carbons to choose from. We could take this hydrogen, in which case our product will be 1-butene, or the hydroxyl group could take this hydrogen, and that's going to give us a product of 2-butene. You see that? 2 possibilities. Usually, it does not form these things in equal amounts. It's not going to be 50-50. And so we've got another rule. We talked about Markovnikov's rule for addition reactions, and then we have Zaitsev's rule for elimination reactions. So the major product is going to be the one that has the greatest number of alkyl groups attached to the carbons of the double bond. So these are the 2 products that we could get from that dehydration reaction. One is 2-butene, where this carbon has one alkyl group and the other carbon on the double bond has an alkyl group. So both of these carbons have one alkyl group. We're looking at the carbons in the double bond. This is the other possibility. Here are the two carbons we're looking at. This carbon has no alkyl groups. This carbon has one alkyl group. So this one's going to be the preferred product because we've got more alkyl groups on those carbons. Does that make sense? You identify what the two possible products are, and then you look at the double bond. And the one where you have more alkyl groups on these carbons is going to be preferred. So here we've got one alkyl group on that one and one on this one. So we have a total of two alkyl groups involved with this carbon-carbon double bond. Over here we have one group. Now granted, that's a bigger alkyl group. That doesn't matter. We only have one group, and so that's not as good. Many organic reactions can go both forward or backwards. It depends on the reaction conditions. And this hydration, dehydration, addition, elimination of water is one of those situations. So we can have an alkene being hydrated to form an alcohol. That alcohol can be dehydrated to form an alkene. And whether it goes one way or the other just depends on the reaction conditions. And so you can control it to some extent. If you add more water, the alkene hydration reaction has water as a reactant. Adding water, do you remember Le Chatelier's principle? When you make a change to an equilibrium situation, a system at equilibrium, the system will shift to reduce the change and try to restore things. So if we add water, we'll get this forward reaction of hydration to use up some of that water, and will favor the alcohol production. If we remove water, then we're going to favor the dehydration and get more alkenes. Intermolecular alcohol dehydration. So we were talking about intra, within one molecule. Inter is between two molecules. So intermolecular dehydration involves two reactant molecules. And now the product is what's called an ether instead of an alkene. And this is an example of a condensation reaction. Condensation reaction is one in which two molecules combine to form a larger one while liberating a small molecule. So it's not just that you have two molecules sticking together. You have two molecules coming apart and together, and one small molecule coming out. Oftentimes that's water. So here's the generic illustration. So here you have one alcohol, and here you have another alcohol. What's going to happen is we're going to lose the OH from one alcohol and the H from another, and they're going to go off as water. So one of the products is water. What we have left is the oxygen remaining on this carbon will bond to the carbon on this side. And this is an ether. An ether is a compound which has an oxygen between two carbon atoms. So here's a specific example, an intermolecular dehydration of ethanol. So here's one ethanol molecule and here's another ethanol molecule. We're just drawing them with their hydroxyl groups facing each other. We're going to take the OH from one, the H from the other. That produces water, and what we have left is these two molecules stuck together as a larger molecule. This only works with primary alcohols. If you try to do this with secondary or tertiary alcohols, you're going to get the dehydration, the intramolecular dehydration, you're going to get an alkene instead. And this is going to happen at lower temperatures. So with the primary alcohols, if we want to have this condensation reaction, then we need to keep the temperature lower. If we want the intramolecular dehydration to form the alkene, then we want to use a higher temperature. So let's do some practice exercises. Predicting the reactant when given the product. So it says identify the starting alcohol from which each of the following products was obtained by an alcohol dehydration reaction. Remember, we had two different types of those reactions that we looked at. So here we have an alkene product. So that's going to be from the intramolecular, the first one, right? Because the second one made an ether, and this is not an ether. So where did this double bond come from? It came from removing a hydrogen and a hydroxyl group, right? So to predict the reactant of this, we can go in here and get rid of that double bond, and then we have to put a hydrogen on one side and a hydroxyl group on the other side. Because when it undergoes that dehydration, these guys are taken off. Now, could the hydroxyl group be on the other carbon? Well, let's try it. What if we put the OH over here and the H over here? Now, when we dehydrate that, we're going to lose this OH and this hydrogen, or one of these. You could have two products, right? And so we could end up with CH3, CH double bond, CH, bless you, CH3. That would be one of the products from this reactant. You see that? The hydroxyl group's in the middle. We could take this hydrogen off with the hydroxyl group, and we would get one with a double bond in the middle. That's not what we ended up with, though, was it? It had the double bond over here. Which is preferable? Let's see. Let's erase this. So those are our two possible products if we put the hydroxyl group on the second carbon. Which of these would be preferred according to Zaitsev's rule? We're going to look at the carbons in the double bond and see how many alkyl groups are there. Well, in this one, how many alkyl groups? Just this one, right? Am I losing you? You look dazed. And in this one, here are the two carbons in the double bond. We've got an alkyl group here and an alkyl group there. So this guy wins. That's the preferred product. But that's not the product we were given. So it must be that the OH was over here and the hydrogen was over there. Because otherwise we would have ended up with a different product. You follow that? No?
Not really.
Not really. Anybody else not really? Okay. Let's do this. Okay, so let's make sure I've got the color that we can see. So we've got this guy. CH3, CHOH, CH2, CH3, and we've got this guy, CH2, OH, CH2, CH2, CH3. Now, where did I come up with those guys? The product that we were given was this. Let me double check that I'm doing that right. I don't want to go back a slide because then I might lose what I just wrote. So our problem is that this is our product. And we know that we got that from an alcohol dehydration. So that coming from an alcohol dehydration, that means that we're going to have, if we're working backwards, we're going to add an oxygen, hydrogen, a hydroxyl group to one of those carbons with the double bond, and we're going to add hydrogen to the other. So if we put the hydroxyl group there and the hydrogen group there, that gives us this first one. You see that? It's just, this one's going up instead of down, sorry. But here the hydroxyl group is on the second carbon. The other possibility is to switch these and have the hydroxyl group over here and the hydrogen there. Do you follow me? Okay, so this is the product. We're trying to find where it came from. So these are our two possible reactants. And so let's take these guys forward and see what happens with them. So if we take this with sulfuric acid and 180 degrees and do this dehydration, we're going to remove the hydroxyl group and a neighboring hydrogen. Hydrogen on a neighboring carbon. Well, it could be this one or it could be that one. So let's write both of those products. If we take the hydrogen off the first carbon, we'll get CH2, double bond, CH, CH2, CH3. You see that? If we take the other hydrogen, we'll get CH3, CH, double bond, CH, CH3. That reactant has two possible products. This is the product we're looking for, right? That is the same as this guy down here. But this is also possible. And we have to look at Zaitsev's rule to see which of these is going to be more. Zaitsev's rule says, let's look at the double bond, look at the carbons involved, count the number of alkyl groups. Here we just have one. This guy, we've got one here and one there. I just did it again. So this guy wins. So the preferred product of that reactant is this. And this one, there might be a little bit, but not so much. So that tells us that this is not our reactant, because that would give us the wrong product. The second one, when we do the same thing with the acid and the temperature, we're going to take off the hydroxyl group and a hydrogen on the neighboring carbon. There's only one neighboring carbon. And so we're going to get the product that we want. We're going to get CH2, double bond, CH, CH2, CH3. Does that make more sense now? No?
I'll just have to read it or something.
Yeah, maybe something that you just kind of have to play out, work it out for yourself, and come back on Wednesday and ask questions. Because I can read this stuff in a book, but I need to get my pencil out, and I need to start messing with it. And watching somebody else do it and talk about it is easier than reading it in the book, but it's still not the same as actually trying to do it yourself. So let's do this next one, B. So again, we have an alkene. So this is coming from an alcohol dehydration. And so we've got two possibilities. We could have We could actually, push the right button here. That would be good. We could have the OH here and the H here. Or we could switch those. If I switch where I put the OH with the H, is it the same molecule or a different molecule? So that would not be a double bond anymore. How would we name that? Sometimes naming can tell you if it's an isomer or the same compound. Well, we've got 1, 2, 3, 1, 2, 3, 4. So we've got 4 carbons as our longest chain, and that would be butanol. And we would number this so that the hydroxyl group is on carbon number 2. So this would be 2-butanol. And then we've got 2 methyl groups, right? So this would be 2-methyl, and that's 3-methyl. So 2,3-dimethyl. Butanol. It's the name of that guy. Now, if we switch this and let's get rid of that and put the OH over here, does the name change? No. We're just looking at it, flip-flopped, right? We would still have 1, 2, 3, 4 carbons. We would just number it from the other end. It would still be 2-butanol and still have 2,3-dimethyl. That's the same. There's only one possible reactant that could have made that product, and that's this one.
When you name it, why don't you account for the single hydrogen?
Because we don't name the single hydrogens. Because there's always hydrogens on carbons to make up the 4 bonds. Because we could draw him down here. So that's the starting alcohol for that one. Let's look at this one. Now, what's different about this one? There's 2 things. There's the temperature, and there's the type of compound that the product is. Is this making an alkene? Is this product an alkene? Is there a double bond? No. No double bond. And the temperature here is 140 instead of 180. This is the condensation reaction, the intermolecular. So we've got 2 molecules, 2 alcohols, and we're taking OH from one and H from the other. So trying to draw with an eraser is just really not very effective at all. So there's the O, and so what I'm doing is I'm gonna break this on one side of the oxygen, doesn't matter which side, and I'm gonna just pull them apart and leave a little space. So these are the 2 pieces that got stuck together to make this guy, right? So here we have 3 carbons. The oxygen is going to have been on one or the other, and then here we have 3 carbons. Well, the water came from this space right here. It was a dehydration reaction, eliminating water. So the H came from there, and the OH came from there. And when this dehydrated, these guys were taken out, and then this guy pushed over and this guy pushed over, and they made this bond. On this one, no, it doesn't, because it's the same on both sides. And I don't think we're going to get into ones where they're different. If this side was, C6 and this side was C3, yeah, it would matter, but I don't think we're going to go that deep. We're just going to look at these symmetrical ones. Because if I cut it over here, I'd still have C3 on each side, and I would still end up with the same products. It's 2 molecules of one propanol. Any questions?